Suppose if you put n is equal to 0, then this is a0 is equal to 2 to the power of 0 is equal to 1. an plus 1 is repeated in terms of an itself, that is called as the recursion definition. So when a sequence is defined recursively, mathematical induction can be used to prove the result about the sequence. After getting the first term, each term of the sequence can be defined from its previous terms. Hello dear students, welcome to this session of Discrete Mathematics class. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram, First Grade College, the Temple of Excellence. In this session, I am going to discuss regarding a very simple concept, that is recursive definitions and the structural induction. So in the previous class, we have discussed regarding the mathematical induction. Now in this session, I am going to discuss regarding the structural induction as well as the recursive definitions. Now let us know what is meant by recursive definition. Recursion means nothing but the repetition. That means sometimes it is difficult to define an object explicitly. So therefore it may be easy to define this object in terms of itself, repeated. So by a object can be defined by itself is called as a recursion. So this process is called as a recursive definition. That is called a recursion. That means an object can be easily defined in terms of itself, that is called as a recursion. Now let us come to the mathematical definition. So now let us consider, we can use recursion to define the sequence, functions as well as the sets. Any sets or a function or a sequence can be represented with the recursive definition. Now let us consider, for example, an is equal to 2 to the power of n for all n is greater than or equal to 0. That is, for all n is equal to 0, 1, 2, etc. So let us define an is equal to 2 to the power of n. So for all n is equal to 0, 1, 2, etc. Now here, if you put a is equal to 0, if you put what is defined, an is equal to 2 to the power of n. Now suppose if you put n is equal to 0, then this is a0 is equal to 2 to the power of 0 is equal to 1. Now put n is equal to 1. So then this becomes a1 is equal to 2 to the power of 1 is equal to 2. Now put n is equal to 2. That is a2 is equal to 2 square. 2 square is equal to 4. If you put n is equal to 3, then this becomes a3 is equal to 2 cube. 2 cube is nothing but 8. So if you put n is equal to 4, then a4 is equal to 2 to the power of 4. That is 2 to the 4, 4 to the 8, 8 to the 16. So this can be written as, therefore the sequence can be written as, for n is equal to 0, 1, 2, 3, etc. Then the terms of the sequence an is equal to what we got, 1, 2, 4, 8, 16, etc. So 1, 2, 4, 8, 16 and 32. This is an example for a recursive sequence. So if an is equal to 2 to the power of n, then the terms of the sequence we are going to get it as 1, 2, 4, 8, 16. So after giving the first term, each term of the sequence can be defined from the previous term. So after getting the first term, then each term of the sequence can be defined from the previous terms. So that means according to the definition, it may be easy to define this object in terms of itself. So here this can be defined in terms of an itself. That is, after defining the sequence, after getting the first term, then the previous terms can be, yes, after getting the first term, each term of the sequence can be defined from its previous term. Suppose here, what is the first term? What we got? a1 is equal to 1. If a1 is equal to 1, then the second term is an plus 1. an plus 1 is of the form 2 into a to the an, that is multiple of 2. So here see, a1 is equal to 1. This is the first term, a1 is equal to 1, and the second term is nothing but 2 into a1. So 2 into an plus 1 can be written as 2 times a into 1. So 2 into, if you put n is equal to 1, this is 2a1, that's equal to 2 into 1. 2 into 1 is equal to 2. Next term is n plus n is equal to 2. If you put n is equal to 2, 2 plus 1 is equal to 2 into A2. So A3 is equal to 2 into, what is A2? 2. 2 into 2 is equal to 4 you will get. Similarly, if I put n is equal to 3, n is equal to 4, A4 is equal to what we will get? 2 into A3. That is 2 into, what is A3? 4. That's equal to 8. Similarly, A5 can be written as 2 into A4. That is 2 into 8. That's equal to 16. Similarly, A6 can be written as 2 into A5. That's equal to 2 into 16 is equal to 32. So, this is how we are going to get the sequence 1, 2, 4, 8, 16 and 32, etc. That means, after getting the first term, each term of the sequence can be defined from its previous term. Each term can be defined from its previous term, and therefore here A1 is equal to 1 and AN plus 1 is equal to 2 times AN. So, therefore, according to the definition, the object can be repeated in terms of itself. It is easy to define this object in terms of itself is called as the recursion. Therefore, here AN plus 1 can be denoted as 2 times A1. So, AN plus 1 is repeated in terms of AN itself. That is called as the recursion definition. Now, you got an idea regarding recursion. So, this is an example for a recursion. So, A1 is equal to 1 and AN plus 1 is equal to 2 times AN. So, that means after getting the first term, each term of the sequence can be defined from the previous term. Now, let us take another example. So, when a sequence is defined recursively, mathematical induction can be used to prove the result about the sequence. So, in mathematical induction, what is the procedure? So, we are going to verify the given statement by considering the value of n is equal to 1 and by assuming that the statement is true for some positive integer k, which implies it is also true for k plus 1. The same procedure we are going to use here. The mathematical induction can be used to prove the recursion recursively, that is, the result about the sequences are, let us consider, let P of k be the proposition about A at k. The basic step is verifying the validity that P of 1 is true. That means verifying P of n is true for n is equal to 1. So, that is verify P of 1 is true. And the inductive step, this is the basic step. The basic step is verifying P of 1 is true. That means verifying the statement is true for n is equal to 1. That is the basic step. And the second inductive step is show that for all k is greater than or equal to 1, P of k is true implies P of k plus 1 is also true. So, in the inductive step, what we are going to take? So, for all k is greater than or equal to 1, P of k is true implies P of k plus 1 also true. Now, assume if f is a function with a set of non-negative integer as its domain. So, we have two steps. The two steps to define the function. The basic step is specify the value of f of 0, and recursive step is given rule for f of x using f of y. Just give a rule for f of x using f of y where this y lies between 0 and x. So, a rule for f of x specifying the value of f of y where y lies between 0 and y, that is 0 less than or equal to y less than x. Such a definition is called a recursive or inductive definition. This is nothing but this definition is called as recursive definition, or it is also called as a inductive definition. Now, let us consider an example. Suppose if f of 0 is equal to 3, then f of n plus 1 is equal to 2 times f of n plus 2 for all n greater than or equal to 0. This is the problem given. So, what is the problem given? Let us consider the problem. This is the question. F of 0 is equal to 3, then f of n plus 1 is equal to 2 into f of n plus 2 for all n is greater than or equal to 0. Then what is to find? Find the value of f of 1, f of 2 and f of 3. Now, what is given? F of 0 is equal to 3, f of 0 is 3 and f of n plus 1 is equal to 2 into f of n plus 2. Now, for all n is greater than or equal to 0. So, let us take n is equal to 0. If n is equal to 0, then this becomes f of 0 plus 1 is equal to 2 into f of 0 plus 2. So, this is which implies f of 0 plus 1 is 1, f of 1 is equal to 2 into, what is f of 0? 3 plus 2, that is 6 plus 2 is equal to 8. The first f of 1 is equal to 8. The sequence is 8. First one is 8. Then next, if you put n is equal to 1, then this implies the function of n is 1 plus 1 is equal to 2 into f of 1 plus 2. So 2 into, what is f of 1? F of 1 what we got is 8 plus 2. So 8 2s are 16 plus 2 is equal to 18. So the second term is 18. And similarly, if you put n is equal to 2, if you put n is equal to 2, then this becomes f of n is 2 plus 1 is equal to 2 into f of 2 plus 2. So that's equal to 2 into f of 2. What is f of 2? F of 2 is 18 plus 2. 18 into 2 is 36 plus 2, that's equal to 38. That's equal to 38. So like that we are going to get. So therefore, the value of f of 1 is 8 and the value of f of 2 is 18 and the value of f of 3 is equal to 38. This is how we are going to find the values of using recursive definition. That's it. This is the example for a recursive relation, right? Okay, hope you got an idea regarding a definition recursive relation. Now let us take another example. Give an inductive definition of the factorial function f of n is equal to n factorial. Now let us give an inductive definition. So they will ask in the examination, give an inductive definition for the factorial function f of n is equal to n factorial. So as we know, n factorial is nothing but n into n minus 1 into n minus 2, n minus 3, etc. That is 5 into 4 into 3 into 2 into 1. Okay. Now what we are going to get? So let us see. The basic step is find the value of 0, f of 0. F of 0 is equal to 1. F of 0 is equal to 1. And the recursive step is find a recursive formula for f of n plus 1. So f of n plus 1, since f of 0 is 1, f of n plus 1 can also be written as f of n plus 1 is equal to n plus 1 into f of n. F of n plus 1 is equal to n plus 1 into f of n. Then what is the value of f of 5? So once if f of n plus 1 is defined as n plus 1 into f of n, then what is the value of f of 5? See, f of 5 can be written as, here f of 5 is 5 into f of 4. See here f of 5 is equal to 5 into f of 4. So 5 into f of 5 is equal to 5 into f of 4, that is 5 into f of 4. F of 4 can be written as 4 times f of 3, because what is the formula? F of n plus 1 is n plus 1 into f of 1. So 4 plus 1 is 5. 4, n is equal to 4 here. So if you put n is equal to 4, then this f of 5 can be written as, so f of 5 can be written as f of 5 is equal to, so here it is 4 plus 1, 4 plus 1 into function of 4. So that is nothing but 5 into f of 4. 5 into f of 4. Again, if you put n is equal to 3, then what happens? So 3 plus 1 is 4 into f of 3. Again, if you put n is equal to 2, 2 plus 1 is 3 into 2 times f of 1. Again, if you put n is equal to 1, then 1 plus 1 is 2 into 1 times f of n. So therefore, in general, we are going to get 5 into 4 into 3 into 2 into 1 into, since what is the value of f of 0? Since the value of f of 0 is given to be 1, so therefore the factorial of 5 factorial is 5 into 4 into 3 into 2 into 1 is 120. In general, you know what is the factorial of 5? 5 factorial is 5 into 4 into 3 into 2 into 1. What is this? 5 4s are 20. 20 into 3 is 60. 60 into 2 is 120. So using the recursive definition, so f of n plus 1 is equal to n plus 1 into f of n. So the value of f of 5 can be written as f of 5 is 5 times f of 4. 5 into f of 4 can be written as 4 times f of 3. So f of 3 can also be written as 3 times f of 2. 5 into 4 into 3 into f of 2. F of 2 can be written as 2 times f of 1. F of 1 can also be written as 1 into f of 1. 5 into 4 into 3 into 2 into 1 into f of 0. What is f of 0? Since the first step is given, f of 0 is equal to 1. So the answer we are going to get it as 120. This is how we are going to find the factorial of f of phi using the recursive definition. So first convert f of n, convert the value of f of n plus 1 as f of n plus 1 is equal to n plus 1 into f of n. Okay, this is the best example. Now let us come to the next example. Assume a is a non-zero real number and n is a non-negative integer. Suppose if a is a non-zero real number and n is a non-negative integer, give a recursive definition of a to the power of n. So this is also an important for 5 marks. So and assume a is a non-zero real number and n is a non-negative integer. Give a recursive definition of a to the power of n. So let us write the basic step. What is the basic step? F of 0. Find f of 0. F of 0 is nothing but, since what is given, a to the power of 0, put a raised to 0 is equal to 1. So f of 0 is nothing but a to the power of 0, a to the power of 0 is equal to 1. So a raised to 0 is 1. Now what is the recursive step? The recursive step is find a recursive formula for f of n plus 1. So f of n plus 1 can also be written as a into an. So that is a into a to the power of n. That is nothing but a into f of n. The recursive definition can be written as a into a to the power of n. So that is nothing but a into, what is a to the power of n? Since a to the power of n is nothing but f of n. F of n. So f of n plus 1 is equal to a into f of n. Then if n is a non-negative integer, so n is greater than or equal to 1. If you put n is equal to 1, 2, 3, 4, 5, etc., you are going to get a recursive sequence. That's it. Now let us come to the next problem. What is the next? Give a recursive definition of sigma k is equal to 0 to n a k. Sigma summation k is equal to 0 to n of a k. Now what is the basic step? Find the value of f of 0. F of 0 is equal to sigma k is equal to 0 to n a k is equal to a naught. A naught, that is, if you put a k is equal to 0, that is a naught. K is equal to 0, sigma a k of k is equal to 0 to n, that's equal to a naught. And what is the recursive steps? The recursive step is just find the recursive formula for f of n plus 1. So f of n plus 1 can also be written as f of n plus a into n plus 1. F of n plus a into n plus 1 is a recursive formula for this function f of n plus 1. This is how we are going to express the given recursive definition as f of n plus 1 is equal to f of n plus a into a n plus 1. Okay. Now let us come to the next concept. In some recursive functions, the value of the function of the first k positive integers are specified. So a rule is given to determine the value of the function at the larger integers from its value at the sum of the preceding k integers. Now let us take an example for that. Suppose if f of 0 is equal to 2 and f of 1 is equal to 3, then find the value of f of n plus 2 is equal to 2 times f of n plus f of n plus 1 plus 5 for all n is greater than or equal to 0. Now what is given? F of 0 is equal to, f of 0 is 2 and f of 1 is equal to 3. Now so just to find out the value of f of n plus 2 is equal to 2 times f of n plus f of n plus 1 plus 5 for all n is greater than or equal to 0. Now suppose if you put n is equal to, 0, then this becomes 0 plus 2 is 2. F of 2 is equal to 2 times f of n is 0 plus f of 0 plus 1 plus 5. Just put n is equal to 0. Then f of 2 is equal to 2 into f of 0. What is f of 0? F of 0 is 2 plus f of 0 plus 1 is 1. F of 1 is 3 plus 5. So this is equal to 2 into 2 is 4 plus 3 plus 5 is 8. 8 plus 4 is 12. So that is the value of the function at large integer from its value at sum of the preceding k integers is obtained. So this is how we are going to get the solution. Similarly, if you put n is equal to 1, then this becomes f of 1 plus 2. F of 1 plus 2 is 3. So 2 into f of n is nothing but 1 plus f of n plus 1, that is 1 plus 1. 1 plus 1 is 2, f of 2 plus 5. So 2 into f of 1. F of 1 is equal to 3 plus f of 2. F of 2 is equal to 12 plus 5. So that is equal to 2 3s are 6. 6 plus 12 plus 5. 12 plus 5 is 17. 17 plus 6 is equal to 23. So like this, we are going to get the values for the sequence. F of n plus 2 is equal to 2 times f of n plus f of n plus 1 plus 5. That's it. Okay. Right. This is also an important problem for 5 marks. Now let us come to the next concept. Using this concept, we are going to explain very important concept that is called a Fibonacci series, or it is pronounced as Fibonacci numbers. We can also find out the terms in the Fibonacci numbers, the Fibonacci sequence. So let us consider the Fibonacci numbers f0, f1, f2, etc. are defined by the equation f0 is equal to 0, f of 1 is equal to 1. So therefore f of n is equal to f of n minus 1 plus f of n minus 2 for all n is equal to 2, 3, 4, etc. So f of n is equal to f of n minus 1 plus f of n minus 2. Now actually, what is the meaning of this Fibonacci numbers or Fibonacci sequence? Actually, the Fibonacci sequence is commonly denoted as f of n. The Fibonacci series commonly denoted as f of n. This f of n will form a sequence, and the terms of the sequence depends on. So this is a sequence in which each number is the sum of the two preceding numbers. Each number is the sum of the two preceding numbers. That is called as the Fibonacci numbers, or Fibonacci sequence is denoted as f of n is equal to f of n minus 1 plus f of n minus 2. Now let us find out the values for this Fibonacci sequence. Now, so here the sequence usually start from 0 and 1. F of 0 is equal to 1 and f of 1 is equal to 1. Okay. Now let us write the value of 2. If n is equal to 2, for n is equal to 2, then what is the sequence we have? F of n is equal to f of n minus 1 plus f of n minus 2. If n is equal to 2, f of 2 is equal to, already we have f of 0 is equal to 0 and f of 1 is equal to 1. So f of 2, this is f of 2 minus 1 is 1 plus f of 2 minus 2 is 0. So f of 1. So f of 1 is 1 plus f of 0 is equal to 0, that is equal to 0. So the sequence, the Fibonacci numbers are, first term is 0 and 1, again it is 1. Next, if you put n is equal to 3, then what you will get? F of 3 is equal to f of n minus 1, 3 minus 1 is 2 plus f of 3 minus 2 is 1. So f of 2 plus f of 1. What is f of 2? F of 2 is 1 plus f of 1. F of 1 is equal to 1. 1 plus 1 is equal to 2. 1 plus 1 is equal to 2. Suppose if you put n is equal to 4, then this becomes f of 4 is equal to f of n minus 1. 4 minus 1 is 3 plus f of 4 minus 2 is 2. See, f of 1 plus f of 0, f of 2 plus f of 1, f of 3 plus f of 2. So what is f of 3? Function of f of 3 is equal to 2 plus f of 2 is equal to 1. 2 plus 1 is equal to 3. Right. Similarly, if we put n is equal to 5, what we are going to get? Let us find out the value of 5. F of 5 is equal to f of 4 plus f of 3. So that's equal to f of 4. F of 4 is 3 plus f of 3 is equal to 2. 3 plus 2 is equal to 5. See here. So etc. So therefore, in Fibonacci sequence, if Fibonacci's numbers are 0, 1, 1, 2, 3, 5, etc. So here, that is 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8 we are going to get. So this is called as the Fibonacci's numbers. So therefore, usually the Fibonacci's numbers are therefore 0, 1, 1, 2, 3, 5. 3 plus 5 is 8. 8 plus 5, 8 plus 5 is 13. Again 13 plus 8 is 21, etc. These are the Fibonacci numbers. That's it. Okay. Let us take an example. Find the Fibonacci number F4. So find the Fibonacci number F4. So actually already we have defined here the Fibonacci number F4 is here. So F1, F2, F3, F4, what we got up to F4 it is 2. So therefore the Fibonacci number F4 is equal to F3 plus F2. F2 is equal to F0 plus F1, that is 0 plus 1 is 1, because f of 0 is equal to 0 and f of 1 is always equal to 1. F of 4 is equal to f of 3 plus f of 1, because we know f of n is equal to, what is f of n? F of n is equal to f of n minus 1 plus f of n minus 2. So f4 is equal to 4 minus 1, 4 minus 1 is 3 and 4 minus 2 is 2, f of 3 plus f of 2. So similarly f2 is equal to, f2 can be written as f of n minus 1 and f2 can be written as 0, f of 0 plus f of 1. Since what is f of 0 is 0, f of 1 is 1, 0 plus 1 is 1. Similarly, f3 can be written as f1 plus f2. What is f1? f1 is 1 and f2 is equal to 1, 1 plus 1 is equal to 2, and f4 can be written as f3 plus f2. f3, what is f3? 2 and f1 is 1, 2 plus f2 is 1. So 1 plus 2 is equal to 3. This is how we are going to find the value. So therefore, the values for f of 4 is 0. Yes, f of 0 is 0, comma 1, comma 1, comma 2, comma 3. That's it. This is how we are going to find the Fibonacci series for f of 4. So using this you can find any value. So hope you got an idea regarding Fibonacci numbers. Okay. So this is very important formula. F of n is equal to f of n minus 1 plus f of n minus 2. That's it. So that's all regarding today's session. Let us meet with the different type of concept in the next session. Thank you. Thank you very much.